Hi there, this is session 29 of programming from the very basics using Python. In the last three sessions, I introduced you to functions and went a little more deeper, covering various aspects related to function definition. I talked about how do you define functions with various arguments and how do you call them with different forms of function arguments, be it default arguments, non-default, variable arguments, and all this stuff. And also an addendum session where I talked about the scope of variable, which spilled over to almost like two sessions, right? So we'll continue with some more aspects that I thought is worth noting about functions as such in Python. And this time, first thing I want to focus will be on the concept of higher order functions and the functional programming aspects that Python provides. So let's look at defining function here. Again, let me select the kernel. I keep forgetting that. I'm sorry for that. I think I need to use another kernel. Yeah, this is the one. That's right. Let's say I define a function called squared list, which sort of I did in the earlier session, but this time I'm not going to use comprehensions. I'm going to do it manually just to prove a point. Okay, so I'm going to take some values as an argument. And all this would do is, assuming that I provide a collection of values, maybe a list of values, it has to square all the numbers in that list and return a new list. You can do that in a one-liner using comprehensions, but hang in there because I'm teaching you something new. So I'm not going to use comprehensions just because I want to focus on other aspects now. So this is not something that you want to use in practical sense. It's just to learn how higher order functions work. Okay, so I'm just explaining that. So right now, I'm just going to create a result is equal to empty list. Start off with an empty list. And I would just say for v in values, I could just use result dot append of v. Result dot append of v. So this will, okay, I'll just use v into v. I forgot that. Yeah, v into v. And then ultimately, I can return result. To call this function, I'll just use maybe, squares or s is equal to square list of, I can pass a list in here directly. And if I try to print s, you can see this, all numbers are squared. I can remember that square of 11 is 121. It's very easy to remember. I guess even 22 must be 484. It looks very symmetrical. 33, 1089. I would believe that. And 44, 1936. So you can see that result is an empty list. For each value or each element or each item in values, it's going to multiply that item with itself, which will give you a square. And I'm appending that to result list. And ultimately, I'm returning result. It's pretty straightforward. Nothing new here. The problem with this function design is there are two things it does. One, it has to iterate over each item of a collection, pick the values. And after that, it has to square those numbers and then store it in a result. Okay, actually three steps, right? Three major steps you can think of. Among that, squaring a number is the major part. Now, let's say I don't want to square these numbers. I want to cube them. I could actually create another function which looks pretty much identical to this. And let's call this as cube list of values. Everything looks identical. The only thing that changes is maybe you want to just cube this number. One way is you can say v into v into v, or you can also use v double asterisk 3, v to the power of 3, right? Item to the power of 3. I think it's a power of operator, which I'm using. And when you run this code, as usual, you can say c is equal to cube list of maybe the same numbers this time. And I'll try to print c, and you can see the outcome of this. The squares of numbers, cubes of numbers given out as two different lists, returned as two different lists. Now, when you look at this function definition, you'll see a lot of pattern in here, which looks pretty much redundant. You can see that, right? Result is equal to empty list for v in values, result dot append. The only thing that changes is the argument that you're passing to append. That's it. Everything else is same. So there's some amount of generic code that is there here. code that's quite generic. And the specialized code is that v into v or v to the power of 3, or maybe if it's a string, I want to, let's say, convert the string to uppercase. If it's like list of strings and I want to convert each string to uppercase from a list. All these are common patterns, right? Now, you can actually separate these concerns nicely using what we call as higher order functions. I'm going to show you how that can be done. I'll copy this whole cell again, but I'll make some changes. To begin, I will create this as, rather than calling a square list and cube list and all this, I want to rename this function as, let's call this as apply. Applying something, right? Or I can say perform, whatever you can call it. I don't need this version. And here, I'm just going to take fn of, and what is this fn, you might ask me? This will be a variable which will be taken in as a parameter. I'm just going to call fn here, followed by values. And now I'll define two separate functions. One is square of x, which returns x into x. Another function, which is cube of x, which returns x to the power of 3. Let's say the rest is 3. To call this, you can just call, you can say s is equal to apply square on this list. I'll use some small numbers this time. Okay. And I'll repeat this. I can also try cube, where the only thing that'll change is apply of cube here. And now when you try to print both S and C, I'll try to separate it by spaces and new line, sorry. And now we can see the outcome of it. Okay, the squares of numbers, they're squares of numbers. And the cubes are the same numbers, cube of 2 and cube of 4 and cube of 6, 5, 8, and 7. You can see them all working. Now, what you look at the design here is this. In the earlier code, I had a lot of repetition of code here, right? This whole logic was repeated. So when you see a pattern where you have a lot of functions which are pretty much doing the same thing, but some minute changes, right? The only minute changes, whether you want to square a number and cube a number, that is what is changing, but everything else, the overall logic that you see of iterating over values, getting them as such, once you square them or cube them, you append it to a result and then return result, right? That's a very generic code. And that generic code is flushed out in this function called apply. You can see that logic in here. But here's the thing. The only thing that changes is whether you need to square or cube or maybe perform anything else. That is separated into separate functions which are there here. These are pure functions, right? And this function, which is defined like the square or cube, is passed as one of the argument. You can see I'm not calling square. What am I doing? I'm passing square by reference. Function names are references to function objects, right? We learned that much earlier, the first series of the functions, 3 sessions earlier, right? So when I just refer to square, I'm referring to a function object. And that function object is passed on as the first parameter called fn. So what apply sees as fn is nothing but the square function. So when you call fn with in this particular code, apply is invoked, passing square as an argument, and this square goes in as fn here, and this fn function is called by this generic function, right? And whatever that fn returns, I'm appending to result. This gives you a lot of flexibility. Maybe tomorrow you want to say, no, I want to find square root of a number, may not be square. So I can just create a function called square root. Let's call this qrt of x and then maybe return x to the power of 0.5. And all I need to do is just call it like this. So I define this function and then I call it this way. Maybe I could just say print apply. I'll just do it in a separate line. I think I'll say sq is equal to apply of sqrt followed by some numbers, the same numbers I'll repeat. Maybe I'll just copy this cell. Let's copy this list. Sorry. I didn't print it, of course. Sorry. Let's print this. And I can see square root of 2, square root of 4, square root of 6, square root of 5, 8, 7, it goes on. So what you observe here is an extensive reusability, right? So a lot of generic features which many functions are going to be having generic logic. You flush out that generic logic into a separate function. And what is different about each function? What logic is different in each functions? You keep them separate. It's called separation of concerns, right? You're separating the concern of iterating over values, getting each element from them, and then the job of performing some activity, transforming them, is done by these functions. And ultimately, what is a transformed value? You're appending to the result and you're returning result from it. So this function, a function which is like this, is also called as a higher order function. What are higher order functions? Higher order functions are functions that take another function, preferably a pure function. It's not compulsory, but it's preferably a pure function as one of their argument and decide how to invoke them or when to invoke them, right? So that's what higher order functions do. And this is a very intricate concept of functional programming. So if you look at functional programming languages, they emphasize more about a higher order function that takes one or more functions as arguments and decide how to call them or when to call them based on their own logic, based on some generic logic. And these specialized functions which are being passed as arguments do the actual work. But these functions are now completely separated out. The square function is known to square just a number, but I'm able to use that square with another function called apply, so I can apply the square function on a collection and return result, right? So you can see how I have separated concerns of managing a list separately in another function and performing square of a number, cube of a number, square root of a number as separate small functions. So this is what you should know about higher order functions. You can use it in many ways. So this applies so generic. There are no types associated. Do you see any types here? Does it say that I need a integer or float or anything? Nothing. None of this stuff. It's very generic, right? So I can use it even in scenarios like let's say I'm going to have some users is equal to, let's assume collection of users. I'm just going to put some names here. The usual names which I can sort of recollect. Okay, I just live with this. This many names. That's enough. Now this time what I can do is I can create another function. Let's call this 2 upper of s or 2 upper of n, let's assume, which just returns n dot upper. It's just a function that given an argument, preferably a string, it calls that string object dot upper. If you pass a non-string value, it's going to fail, obviously, because only string object has upper. So no validation in here, okay? It's just as is, plain. Now, I can apply this. So this 2 upper works for one single string. I obviously cannot call 2 upper of users, right? It doesn't work. It'll throw an error. You can see it. Tuple object has no attribute upper because it tried to call, I passed a tuple here. This users is a tuple of strings. I'm passing a tuple as an argument here as n, and tuple does not have upper method. Only the strings inside this tuple have it. So you need to do traversal or iteration of the tuple to get each string and invoke upper method. And that job is done by apply. Now I can do this. This won't work, but however, I can do this. I can just type maybe, I can just say result is equal to, or I can call this u names is equal to uppercase names, let's assume. Not a good naming convention, but it's okay. In this case, u names is equal to I can just call this as apply of to underscore upper and then pass users. Now print unames. This works. You can see here. This is what a simple example that explains the true essence of higher order functions. Right? Now the fact is that these higher order functions, they tend to be very generic. They tend to be very generic. Now let's assume that if at all I have some function that not a function, a data that does not match these elements. Let's assume that when I'm calling users here, for now one of the elements is 10. You can see that when I try to call this, it raises an exception. And there are ways to handle it, but I will talk about that in a moment. Just keep that in one side in your mind. I'm going to come back to this and tell you what are the things you can do with it. That's the major part of this video. But before I directly jump onto this to explain how to make things work, and I need to tell you about another aspect which is just came to my mind. Forgot to cover that. Is these functions. Do you see these pure functions? There is something common about these functions, right? Square, cube, sqrt, even that to upper function which I have defined in here. There's something common about them, about their pattern. Say. What is common? If you look at the function body, all you have is just one expression. They're returning the result of one expression. That's what they do. There's nothing else. There's no other statement. No validation, nothing. I'm not doing any of the stuff. Give me x, I'll return x into x. Give me x, I'll return x to the power of 3. Give me x, I'll return x to the power of 0.5, which is the square root. And here, give me n, I will return n dot upper. So given an argument, you're trying to do some transformation based on that argument and based on an expression and returning the result. That's it. Nothing more. No other logic. When you have functions like these can be sort of optimized. I'll tell you how. Let's say I have a function called square. I'll come back to this another cell. One way to define a function like square is square of x, which returns x into x. You can see that square is a function object. You can say type of square is a function object. And you can also call it by calling square of 2, for example, and it will return 4. You can see that. This part of the string, this whole thing, is a result of this one. I'm trying to print square as a string. When you try to print a function object as string, the string representation of function object will be function in angular bracket function name at so-and-so location. Type of square, undoubtedly it belongs to a function. That means the square is a instance of a function class. Functions are objects, so there's a class for function. I think I talked about that in the first session about defining functions, right? So just trying to reiterate that. And I'm able to invoke this function as usual. Square of 2 returns 4. You can define a function like this kind of function by another means. You could actually use, this time I'll name it as sqr is equal to lambda x colon x into x. Now is the time I'm introducing you to lambda expressions. So in fact, before I even dig into it, let me tell you about these lambda expressions. This has been one of these big checklists of various modern popular languages. Lambda expressions existed from the earliest of Python I know about. I think from Python 1.5 I knew it, but it's been there for a long time. It's nothing new. Python had it from the 90s. And there's nothing new in Python. This lambda is a concept that's taken from pure functional programming languages like Lisp. Lisp is known for having lambda expressions, right? There's a language like Lambda also. I heard about it. There's a functional programming language called Lambda. I think Clojure is also having that. So all the functional programming languages boast about this feature. What is this? This is an anonymous function. A function that is created out of an expression, by the way. You can see this. When I say def square, what am I doing? I'm defining function. And definition is a statement. It is not an expression. You cannot put this def square of x, return x into x in a right hand side expression. That won't work. Try it out. It will not work. If we try doing this, we just say a is equal to def square of x, return x into x. Some of you might think, can I not do this? It's a syntax error. So in Python, def is a statement keyword. Just like del, just like import. I told you all the statements. They are not expressions. Reiterating that. Now, that's why this won't work. But however, using a keyword called lambda, you can create a function dynamically as a right-hand side expression. But there is a small limitation in Python. That's a language syntax grammar limitation, perhaps. The syntax parser has a limitation with that. And this is also conforming in a mathematical sense. There are many other languages I know of. I know about Perl. I know about Ruby. Many of those dynamic languages. You can actually create a function with a huge block of code as an expression. You can do that. In Perl, I can do that. I can say $A is equal to sub, open curly brace, open close curly brace, and have a block of code in it, multi-line code. And they call them as anonymous subroutines in Perl. In Ruby, you have the so-called proc blocks. They can create procedure blocks. I think many languages of that fall into that category. Even JavaScript has it. They call them closures. In fact, the concept of closures, the word closure comes as a function that's created dynamically through an expression returned out to the left-hand side, which can be assigned to a variable or passed on as an argument to something. They're called as closures. Closures are used extensively, even in JavaScript, right? So you'll see a lot of these anonymous functions being created on events. So on events, you create a function directly and that function do something dynamically. That's a very common thing. And these are all functional programming idioms. So you have something to do. You don't define a function beforehand. You define the function at that instant. And this happens. There's a function that you have to call. The function body is right there. So you work on that way, right? There are debates about whether that is readable, maintainable. It's argued. Some people find that completely complicated to maintain. That's what it is. I think the Python world believes that creating code like that is going to make the code more complicated. So they didn't really dig deeper to go ahead and implement that. They thought, let's not worry about that. But the most common use case are functions like these. That is what you can create using lambda. The lambda expression is like lambda will create a new function object. And whatever you pass here will be the identifier that will be used as a parametric variable to that function or argument variable to that function, right? Argument variable. Followed by a colon. And then you have the result of that function, the return value, what this function is written. It's like telling this lambda x colon x into x means I'm going to create a function that given x will return x into x. That's it. You can just have a single expression here. Statements will not work. If you try things like import or if condition or while loop or for loop, none of those work. Can't use any statement keywords in here, right? You can use anything to do with the expressions. You can use a comprehension if you want, which has for in it as part of comprehension. You can also use ternary if expression. That's an expression. Anything that I told is an expression in Python, you can use it. Anything that's categorized as statement, you cannot use it. You can't even do assignments. You can't say v is equal to x and you can't do any of those things because assignments are statements, not expressions. So that's something that you should remember. So lambda expressions are only suitable for optimizing functions like these. How is this going to optimize? You might ask me. At this moment, you won't see any difference. When you do it like this, there's absolutely no difference between defining a function called square or creating a function through lambda expression. Let me show you. I just use print here. Try to print it out. Print sqr and what is that? Okay, type of sqr. And I'll also call it sqr of 2 just to be consistent with that earlier print statement. Because when this function is being defined, there's no name being specified here. When you use def keyword to define a function, whatever you use here, this name, will act as the name of the function object, plus it also creates an identifier by the same name. There's a variable or identifier called square that's created that points to a function object. And that function object will also have a name in it. Remember, we saw that as function dot double underscore qual name double underscore, the under attribute, right? That represents that name, which is done with this definition. But here, this function, the function created by lambda expression is created by lambda. There's no name here, right? So that function is simply named as lambda like this, just to give a hint that this was created using a lambda expression. It's good for debugging. Don't try to change it or do anything. Just leave it at this. This way you know it's created by lambda expression. But it's a proper function because it belongs to a class called function, just like the earlier function did. And you can also invoke it normally like any function like square or so, right? You can do that. And yes, can I take more arguments in lambda? You can. You can say lambda x comma y colon x plus y, and that will work. Maybe you want to create a lambda to add two numbers. You can just say add is equal to lambda x comma y colon x plus y. And now when I try to print, I can just say print add of 10 comma 20 greater than 30. So I told you how you can create a function using a lambda expression. And I also told you the restriction with it, the limitation. The lambda expression is created with a syntax where, so the so-called body, which you see after the colon, should have come up on the same line. This is not a compound statement, by the way, because it's a right-hand side expression. You can't have it in another block or something. There is no indented block supported. So after a colon, you can only have one single expression. That's it. Can't have anything more, right? With that being said, whenever you have a use case scenario like this, where I have created this function called apply, for reliability's sake, I'm just going to copy this cell all over again. I'm going to edit it. I don't have to define all these functions separately anymore. All I can do is apply is a higher order function because it takes another function as an argument. So I can pass on as a result of lambda expression. I can say lambda v colon v into v. You can use here lambda, I can say x colon x to the power of 3. Remember, the variable name can be anything, right? And even the other one, which is there here, which is apply to upper names and all that. Let me do one thing. Okay, I'll do it here. I can just say apply. I don't need to create this function called toUpper anymore. Directly I can use apply lambda u colon u dot upper. And all these works. The most common use case for lambda expressions is in higher order functions. So how is this a little optimal is that I don't need to have a function called square lying around in memory. I will not use it anywhere else. There's a use case requirement where I want to apply squares. I want to apply the algorithm for squaring all the numbers. So I manufacture the square right here using a lambda expression, pass it on to apply as an argument. So apply will get it as fn. It'll do its job. And the result is returned. This particular function which is created has no more references, so it'll be garbage collected. So these are like temporary use and throw functions. You just use them when you want, and once this entire statement completes, or this expression completes, whatever function that's created by the lambda expression is disposed of, because I believe there'll be no more references at this moment, is disposed of. So this is the use case. You'll find in the practical examples, apart from this small program I showed you, you'll find lambda expressions used in places like pandas. I found in pandas they use it. If you use pandas for data analytics, most of these aggregation functions take lambda expressions. You can pass lambda expressions there. Most of the aggregates will take a function to be called to compute the aggregates, right? So there you can pass on lambda expressions if you want to. It's used in various places, right? It's you know how it works. You just want to create a function dynamically on demand to be passed as an argument to a higher order function. You can compose it using lambda expressions. And that's what you should know about it. Now coming back to the higher order functions I told you, is I talked about one of the limitations, remember? Let me just copy this cell. This cell, I think I can use this. This was anyway throwing an error because there was a 10 here, right? If you remove this, I think it will work. Now let me copy this code one more time. Now, assuming that I want to square numbers, so I create a function for squaring numbers here. Create a function this way, right? To square all the numbers. But this will work assuming that all the arguments to a list are numbers. If you have a list that's got a non-numeric value which cannot support multiplying with itself, then it will raise an exception, right? For example, if I'll print s here, I'll say square, I'll say s is equal to and s here. For now, I think you can see this working. But then in this particular list, if I add a value which is a string like this, throws an error. Why? Because you can see the error is thrown in the apply. Oh, is it in apply? No, it's in the function. You can see this. Can't multiply a sequence of non-int of type string. That means you can try to run this lambda expression. This lambda expression, v into v, it didn't work because you cannot multiply hello with hello. You can multiply 2 with 2, you can multiply 4 with 4, you can multiply 6 with 6. But the moment you try multiplying hello with hello, that throws an error, and that error is thrown by that lambda expression that is caught in here. You can't append that value to a function because an error is caught here, and it throws and it shows up. One problem here is that when you use a lambda expression, when you look at the error trace back, it may not look very obvious and where the error is. That's one limitation. So there are people in the Python community who are not very encouraging about usage of lambda expressions. I should warn you that. And I would fall in that territory. So only when you have very simple code, where things are quite obvious, things that don't, the chance of failure is very less, then you can use lambda expressions. But for anything that's complex, like the pandas aggregate and so on, I would not use lambda expressions. I would want to create a function separately and call it. That makes it more maintainable. Always give precedence towards maintainability. So look at this. The error traceback is not very legible. I don't know what really went wrong when you read this, right? Where is failed? I don't know. It shows here append, but append call this. It started from here. It went back to this. Doesn't look very obvious, right? But now, if I had used this as square function separately, create a function called square, an explicit function by name square, and def square of x. I just put return x into x here, and passed on square as an argument. Now things will look more obvious when you look at the traceback. You can see that it failed exactly in this line. Def square of x, return x into x. There's only one expression, so obviously this can be the problem. So you can see that the error is in line number 7. In here, it shows the error is in here. This, I think the line numbers are not enabled for some strange reason. I should enable that. Okay, is there a way to turn it on? Yeah, show line numbers. Yep. Now you need to go and click on this button here. You get a lot of options for a cell. You can turn on line numbers. Actually, if you are using Jupyter Notebook, I think it's available in the top toolbar or the menu bar. In the menu bar view, you can enable line numbers. It's more convenient there, but here you can do it on a cell-wise basis. So you can see at line number 7 is this particular line. Is what is highlighted there. It's an error. So you can very clearly find out. Unlike when you use lambda expressions, it'll fall into the call where you put lambda. So it'll not tell you exactly where it is, right? So you need to figure it out. Now the problem here is that I could not handle this gracefully. It throws an error and I couldn't handle it gracefully. Now, how do you handle this error gracefully? Well, there are two things you can do. You can use a precautionary measure. But I want to make sure this apply function is smart enough while it's iterating over values. You can check if the value is not a number, then fail. Give a more graceful error. Don't call the target function, then give a graceful error. Maybe return, maybe I don't want to throw an error. Maybe I want to store a value 0. Let's say that. So I'm trying to square all these numbers, but the moment I see a non-numeric value in a list, in the result, as a substitute, I want to store 0. Maybe that's what I want to do. Let me try to implement a function like that. So here what I can do, I can check if type of v is not integer. If type of v is not an integer, then I can set result dot append. Let me do one thing. I'll just use r is equal to 0. Else r is equal to fn of v. Or you know what? It's not telling is not. I like to have it like this always. Negated condition checks are sometimes too very confusing. You want to avoid it. If it is a number, call a function. Otherwise, you can set r as 0, and then whatever the outcome, append this to the result. I'm just going to put append of r here, as you can see. So here, r is supposed to be the result of the function call if it's an integer, which means if it's square, you'll get the square of numbers. Otherwise, it'll return 0. R will be equal to 0 if the type of v, the value, is not an integer. And when you run this code now, it sort of worked. We did not really break the program. I sort of gracefully managed the error by making a check. I'm making a precautionary check. I'm trying to check if the value which is there in this list, if it's not a number, then I substitute with 0 instead in that place in the result. Now there's a problem with this design. The problem with the design is, suppose I pass a number which is a floating point. Now that's a problem because floating points can be squared. You can square 5.6 into 5.6. All numbers can be squared, right? You can handle that. You can see 5.6 is also stored up as 0 here. Not a great sign. So how do you make this better? One of the option is you want to change this code. I want to copy this. Okay, I'm creating a trails of all the modifications I'm making. I could say if type of v is int or type of v is float, or better yet, you can say if type of v in either an integer or a float. See, I'm using the in operator here, right? Checking whether type of the item, each item in the list, if it's an integer or a float, you can square them. So you can actually store it. You can compute the square by calling the function. In this case, the function can be called, get the result. Otherwise, set r is equal to 0, and whatever r is based on the type, right? Stored here. Now this will handle floating point. And a floating point can lead to this round off issues. You might want to round it if you want to. That's another story. Let's not worry about that. Now, I handle int and float, but I didn't handle complex. Tomorrow you want to introduce fractions. Tomorrow you want to introduce decimal. There are different numeric types that can come up. Every time there's a new numeric type, this code has to be refactored to handle those each type. So this code is still not very generic. This higher order function is not generic. How do you make it more generic? By applying one of the object-oriented concepts called generalization. Now, what is generalization? Well, it's a big topic. I'm going to keep it as short as possible. I'll be revisiting generalization when I do classes on object-oriented Python, which will be another stream of training sessions, which you'll see me doing after this completes. Now, generalization is what drives most of the things in real world objects, right? In fact, it's an object-oriented terminology. So you heard about this concept called inheritance in object-oriented design. It's mainly got to do with generalization. Some people use inheritance for reusability. That's a horrible design. I would be dead against it. You never use inheritance for reusability. That's a bad design from start. That's a big talk. There's a separate talk I want to make for that. Separate video for that. But I should summarize that the reason why we have inheritance is not for reusability, is to mainly apply generalization. If you want to imply reusability, you should use composition. That's the right thing to do. For people who have some awareness of object orientation, and just clearing the air here. Now, what is exactly generalization? For those of you who are not aware, it's basically this. Let's say I'm communicating to you and I ask you, let's say we're in the classroom, same place. Let's say you're in my classroom and I ask you, give me a pen. I'm not very specific. I said, give me a pen. There are different kinds of pens. We have a fountain pen. We have a ballpoint pen. You might have a felt tip pen or graph pens like ones I have here. The ones I keep showing you. Graph pens like these. These are also felt tip correctly. So there are different kinds of pens you might be having. You can give me any one of that. Because I didn't specify, I need a fountain pen. I said pen. Pen is a base class. Pen is a base class. And all of these, fountain pen, ballpoint pen, felt tip pen, graph pen, maybe markers, whiteboard markers, they all inherit pen. What do you mean by inherit pen? They all follow the common traits of a pen. What are those common traits? What do you use a pen for? For writing. So what do you do with a pen? Let's say, I'm just taking one of the pens in here. Let's bring the other one. Here's a pen. Most pens have this. I know this on my camera. It's not blinking, is it? Okay, let me take a dark pen. This one. Let's take this. This doesn't blink on my camera. I think there's some lighting issues. All right. So I have a black pen here, and if you give me a pen and ask me to write, I have to open first. There's one method: open, write, and then close. Right? That's what this is. That's an interface. What is the interface for the pen? Open, write, close. The primary interface of this pen is writing. Use a pen for writing. Oh yeah, you could use a pen for doing many things, but writing is what it's meant for, right? That's one of the primary trait of any object. Every object has some kind of a primary trait or the primary use case. If I'm using a microphone, I use it to speak. I wouldn't use a microphone to put it on my ear and try to listen to audio on it. No, it doesn't make sense. It's meant for recording audio. I would use a headphone to listen to audio. I don't do anything else. I don't write with a headphone. You don't do that, right? Or I have a mouse here. What do I do with it? Point and click. I will not write with this. So every object has an important use case. Important use case. Or some of you might ask, what do you use a smartphone for? I was a little confused. I was not able to define a smartphone. Because when smartphones arrived, it does way too many things, right? There's a calculator on it. There's an email client on it. There's a video player on it. Right? It has everything. But the primary trait of a phone is to make a phone call. That's why you call it a smartphone. You still use it to make phone call. So today what I define a smartphone as is it's a socialization device. It's an advanced socializing device. That's what I would call it. Because what you do in a smartphone is swipe some YouTube videos or shots and Instagram or whatever. All these are what? The way you're socializing with the rest of the world electronically. That's a different story. I mean, you're no longer going out and meeting people. You're watching them on Instagram Reels. You're not sitting in my classroom anymore. You're listening to me by watching my videos. We're still socializing, isn't it? So it's a socializing device. That's what I call it. Some of you might say, oh, it's a computer. Yeah, it is a computer by implementation, but you don't really code on a smartphone, do you? Nah, it's not. It's painful. You can, actually, but it's painful. Imagine a small screen doing that. Not very convenient. So fine. So I told you that every object has a trait, and it gets a trait from what we call as a base class. A phone is a primary communication device. It's a first device. So we had telegraphs and other things before it, but phone is a primary thing that we all use. It's just more accessible to everyone's house. Well, we never had a telegraph machine in each home. It was very expensive. When telephones came along, telephone lines were set up, and now people can communicate across places without traveling to their houses. Right? We could make phone calls to people living in different streets and different cities through a phone call. And that's how we started communication. Today's generation might not know it, but there was a time when the only means of communication could be maybe writing postals or posts, letters, sent by mail. Today it's email, right? Olden days, you put it on post. But later on, we had postcards and all that. And later on, if you want to have a live communication with somebody, The only way you do it is telephone. Telephones now became more superior. We had mobile phones, things you can carry in your pocket. And now we have smartphones, which not just lets you have an audio call, you can have a video call. You can also socialize via other tools. That's what it is. Ultimately, it's all about communication device. It's a socializing device. Let's say socializing device is a base class, and in that you have phone, you have telegraph, and you have many things, and you can create descendants. Vehicle is a generic class, a base class. And we have different kinds of vehicles. We have two-wheelers, we have four-wheelers, we have trucks, we have many things. We have ships and aeroplanes. All of these are vehicles. The trait of a vehicle is let you transport from point A to point B, or transport any object, or a living being like a human being or anyone, any object, from point A to point B. That's what any vehicle would do. And there's so many of them. If you take even a car as one of the vehicle, which falls in the four-wheeler. Again, in car, you can have a subclass. This is inheritance, right? And cars will have different types. You could have a hatchback, you could have a sedan, you could have a SUV, or you could have the luxury cars, whatever you call it, right? The Rolls Royce kind. I don't know what they call them, saloons and whatever. There are different terms for it. But all of these are subclasses. And then you have one of the cars, or maybe you have an EV, electric car, right? So you have different subclasses. So you have a hierarchy. But if I had to ask you, what car do you own? I'm being very generic. You might have any car. You might have a SUV. You might have a Tesla, or maybe you might have a hatchback. It can be anything. But if I ask you, which SUV do you own? I'm being super general, super specific. You could reply back to me and say, no, I don't own an SUV. I don't own one. You could say that. Or worst case, you could say, I don't own a car. Yeah, in India, we have a lot of people who don't find it a real reason to own a car. We are quite happy with two-wheelers, right? Scooters and motorcycles. And we use public transport if necessary, or Uber. So you could say, I don't own a car. So how do I make it more generic? I can ask, what vehicle do you own? So in such case, it can be either a bicycle, it could be a bike, it could be an exotic motorcycle, or it could be a truck, or who knows, I might be owning a yacht. Can be anything. So you can see about the concept of generalization here. I'm trying to generalize by creating hierarchies of classes. As you go up, you're trying to be very generic. Those are the superclasses or the base classes. And then you have subclass from them, which follow those traits but have different implementations. Different implementations. I told you, you don't do inheritance for reusability. I'll tell you why. How you implement a yacht is very different than how you implement a car. There is zero reusability in them. Zero. How you implement a ship is very different than how you implement an aeroplane. Zero reusability. The only thing common between them, they let you transport from point A to point B. How you operate a ship and how you implement things inside is totally different. There's nothing that's reusable. Or some of you might say, oh, I use nuts and bolts in a ship. I can use a nut and bolts on an aeroplane. That is composition. That is composition. A ship is made up of many things. An aeroplane is made up of many things. That is composition. That's called a hazard relationship. Right? When you're building inheritance hierarchies, you focus on the primary trait of an object. What is the important use case for an object? And a good object-oriented design would always follow a scenario where if you're trying to define a class for an object, you have to make sure that the primary use case for that class, the instance of the class, object, let's say, primary use case for the object, as you define in the class, must be focused to just one use case as much as possible. If not, let's say a class that does logging, it does database connection, it does getting user interface, that's not good. That's not good. The class is doing many things. So the primary responsibility of a class must be focused to as minimal as possible and break it down to other classes. Database connectivity, you have another class for it. You want to do logging, another class for it. You want to build a front end, there's another class for it. That's how you split it across. And then you set up collaboration between them. Collaboration between them. You collaborate. Each class collaborate. This is the core concept of object-oriented programming design. I hope to do a full-blown videos on that. That's in the future. Okay, after I finish this. But I'm just giving you the gist of it. What am I talking about all that? To talk about generalization. Now coming to generalization, here, instead of checking whether the type of an item is specifically an integer or a float, you can see that int, float, complex, bool, they're all kind of numbers. So you can see that numbers are the base class for all these implementations, right? So I need to look for whether they're numbers. So I need to look up the base class for all of them. Well, in the early days of Python, there was no big necessity to use inheritance hierarchy, so it is not very much used or even implemented rather within the Python language. It wasn't there. If you look at all the built-ins back in the days in Python, int was a separate class, float was a separate class, complex was a separate class. They didn't have an inheritance hierarchy. They thought it's like that leads to more structural and design complexity, and they didn't bother with that. But they came out with a hack later on. Actually, this is a side effect. They introduced a concept called type system, also called as gradual typing. I will be talking about that in another session in this series, right? Gradual typing. There's a lot of push into that space. You see some of these things here. It's all okay. When you select any of these things, okay, let's take this. Yeah, now look at that. Variable result colon list. That thing that you see there. In this case, it's very specific here. You can say fn colon any, that's a type. All this comes from modern features of Python called the type system for supporting gradual typing. It's not part of your language runtime. The runtime doesn't care about all that. This is used by the IDEs mainly, primarily, and some tools to aid them to check whether you're following some strictly defined types like you do in statically typed languages. It's called gradual typing. We'll talk about that much later. Okay. Now, in order to support these features, they had to introduce a concept called abstract base classes, shortly called as ABCs. So think of that number is like an abstract base class for all implementations of numbers, whether it's int, float, complex, bool, and many more that's there in modules, a couple of modules, right? So they created that. I think that arrived in Python 3.3 or 3.4. I had to verify that. It came in during that time frame, and it's being followed through. A lot of new features getting added and it's being refined. Now cutting to chase here, if at all I want to check for type, rather than using the type construct, type will return exactly what type an object belongs to. But there is another function, which is a built-in function, which is called isInstance. isInstance lets you apply generalization rules. So isInstance takes two arguments. You can pass v, which could be a variable, which represents some number or something. And then rather than checking whether it's an integer, you can also check up its base class. The isInstance is also called as instance of operator in many languages, or the instance of relationship. What it basically does is, given an object as one of the arguments and given a type as a second argument, it checks whether the object belongs to the type or any of its subclasses. So if I say if is instance of v comma int, it doesn't just check for integer, doesn't just check whether v is of type int. If int has any subclasses, it checks even for the subclasses. Maybe I created my own subclass for integer and called it as positive integer. It'll work. We can use this. So it's a more of a generalization safe operation. This follows one of these principles. It's also called as LSP, I guess. It's called as Liskov's substitution principle. We use that extensively in object-oriented design in language like Java, where we use all this typecasting with classes and objects. Person P is equal to new manager. Manager is a subclass of person. So you can instantiate a manager and assign it to a variable of type person. That's the way it is in Java, C++, and couple of those statically typed languages. But they use generalization rules there by using list cost substitution principle. This is how we do it in Python way, purely in runtime. And I'll show you how it's done. In order to use this particular check, you need to load a module. That module is called, you say, from numbers, import number. Think of number is one of the base classes of all the numeric types that we see here. Like, if you look at int, float, complex, and boolean, they all are subclass of numbers. They're all subclass of numbers. If you want to find out how do you find out who's the base class of int, let's try this. Int dot base. Oh, is object. Doesn't work. It doesn't work. It says an object. Let's try float dot base. It's an object. Let's try basis maybe. Maybe they do it in a multiple units way. No, it's not. Okay. Even now, these are all just instant. They're all the subclass of object, but this number does all the magic, perhaps. I'll show you that. Is instance figures it out. So I can try this here. I can try from numbers, import number here. And now you can say for v in these values, sorry, you can just, rather than checking for specifically int or float, I can just check if is instance of v comma number is v a number. Like I give you this, you ask me, is this a pen? You don't know it because it looks very peculiar. This is a kind of pen that you never used. So is it a pen? I say, yeah, it's a pen. Then you open it up and you can start reading. It doesn't matter what it is, right? So that's pen is like a generic way of representing all the kinds of pens you might be having, right? That's how you see it. Now this makes it so super generic. And this is also called as using generalization. We call it as LSP or list cost substitution principle. I should be a little honest and a little bit humble here because these terms, to be honest, I never learned them in any books. The books that I read is mostly deep down technical. I read it, but never read this conceptual books. And how do I know this? When I was delivering trainings to various companies, and one of the company, when I showed this code, one of the participants waved his hand and said, "Oh, that's LSP. That's list cost substitution principle." Okay. List cost substitution principle. What's that? And that's what he said. It's what it works. And he sure talked about this person P is equal to new manager. And then I did some read up. That's how I learned. So a lot of things I know about Python is because I should thank to a lot of participants whom I trained for the last 15, close to 20 years now. Close to 20, but largely full-time, almost 15 years. So they have refined my thought process. Okay. So if I'm wrong a bit here and there, you can go and check it up. So just search for this keyword. It should be the same. It should be on the same lines, right? So using generalization here. And now in this place, you can try this. You can say if instance of v number and all these things, and try running this. This time, it worked for float. You can try even a complex number. Let's try. I'll just change this one, this 4 as 4 plus 5j. It works. I can add a true here. This works. You add any other data type. Let's say I'm going to put none here. The last argument is substituted with 0. Well, we made this function more generic, right? Now, is this Pythonic? I would argue against it. It is not. Oh my God. You just spent a lot of time telling us how to do this, how to use is instance, v number and all this. Yeah, this is one of the ways of solving a problem, which would be appealing to programmers who come from C++, Java, and many other languages. But you know how you solve this in a more generic way in Python? I'll tell you the problem with this one first. It works with all numbers. Now try this. Try this one out. I'm going to say apply lambda x colon x dot upper. You know what I'm trying to show here? John, Sam, Jones. Whoops. 0, 0, 0. It's not that generic after all, right? Because this is now hardwired to only work with numbers. Maybe the numbers are generic, but what if it's a string? That's a problem. Now, how am I going to make it more generic? This is where I want to introduce you to something called as duck typing. More about duck typing as a terminology and all these things in another session perhaps, because I want to don't stretch this video too long. So I'm going to show you what it is first. Then I'll tell you why it is called duck typing and all the stuff in another video, in another session. There's a lot of history behind it and a lot of things that went along. So this time I'm going to use apply, but I'm not going to use the if condition here at all. No if condition. You know what I'm going to do? Try calling this function. Check if it does not fail. If it fails, set the result to 0. One of the changes you make here, you don't see any reference to types here. Do we? No number, no int, no float, nothing. This is super generic. It's very, very generic. So this takes in a function, takes in a collection, and now it's going to iterate over the collection. It's anyway going to call the function. If the function works on this value without causing any errors, it's going to get the return result of it. It's going to append it into the result. But if it causes an error, it's going to set the result to 0 and do it. So anyways, when you run this code, this works just like before, but in a more generic manner. And this is an example of what we call as duck typing. This term is popularized by Python. I think the credit goes to a veteran Python contributor, plus he is also a serial language contributor. He's worked on many languages. He's a veteran. His name is Alex Martilli. He's contributed immensely to the Python's object-oriented design, I believe. So a lot of other code paths and design features in Python, mostly in the view of object orientation. And he's the one who's created to coin this term, Alex Martilli. And it's based on a poem. It's not a poem, it's a sarcasm by a poet, an American poet whose name is James Whitcomb Riley. I think he's a familiar American poet who lived in the previous century. And I think he made this sarcastic commentary, a political sarcasm, I believe. He said, when I see a bird that walks like a duck, that quacks like a duck, and swims like a duck, I call that bird a duck. A lot of things behind it. But in summary, I should tell you, what duck typing works on is you don't worry about the type of the object. You should not worry about the type of the object. You worry about the actual traits of the object. What do you use a pen for? Writing. So you don't ask for a pen. You don't ask for a pen. Ask you, give me a pen, right? No, that's wrong. I would say, give me something to write. Give me something to write. When I frame that question that way, you can even give me a pencil. I can write with this, but it's not a pen. This is not classified as pen. Actually, this is classified as a pen. Whatever, this one, right? This is classified as a pen. And this is a pencil. But both can be used to write. So, instead of asking you which car do you own or which vehicle do you own, I formulate the question as, how do you travel? Interesting, right? How do you travel? So when I ask you how do you travel, you're focusing on the verb, the trait. So when I say how do you travel, I say, oh, I walk. That's a way to travel. That never comes in the picture of vehicle, right? You're trying to be super generic now. So you don't really worry about the type. You take in that particular argument, pass it on to the function. If the function can square function can multiply a value with a value that has to be a number. Only numbers can be multiplied with themselves. You can't multiply a string with a string. You can't multiply a list with a list. That's going to fail. So the function is going to fail anyways with a runtime error. When you pass a string or a list or a tuple or any other data types, you gracefully handle it. And then say, oh, okay, this object is not compatible. So, okay, this is what it is. There's a joke I make. It's like you have a blender. You put some fruits in it. Yeah, you can blend the fruits and have some fruit juice. Maybe you can put some vegetables in it. And you can also have some healthy vegetable, whatever you call it, juice, right? But you don't want to put some spanner in it. That's a very dangerous thing to do. Never do that. Spanner inside a blender. The blender is just going to jam around and break apart. And then you know that, oh, you shouldn't use a spanner on a blender inside a blender. That's the hard thing you learn. That's exactly what's going on. You pass the argument anyways to the function and expect the function to work, but the function fails. You gracefully handle it and say, oh, okay, this doesn't work. Handle it. That's exactly what try except blocks are meant for. This is a try except block, by the way, the most simplest part of try except block. If you believe there's a statement that can raise an exception in runtime, you can put them inside a try block. If this code does not raise an exception, it just continues as if nothing happened. But if it did raise an exception, the except block is invoked. And this is what will happen, whatever statements you put in here. It's the very simplest version of try except block that I showed you, but I will have another session where I go into more detail about exception handling. When I talk about file IO, I'll give you more details about it that will get more insight. But this is how you apply duck typing. That's why in Python, there are many expressions that do not specifically check for a data type. When you pass an argument to a function, they don't explicitly ask, oh, give me this particular type. Give me that particular type. They don't do that. That's why types are irrelevant. If at all you define a function to work on a list, you assume you pass the list and you start working with it. You iterate over it. You pass a number to it instead of a list to that function. You try iterating inside that function, it's going to fail. Like in here, this apply. Nowhere I mentioned this values must be a list or a tuple or anything. Nothing. I can just do this. I can just say, pass a number here. It is bound to fail. As long as you as a caller here can handle that gracefully, that's fine. That's how it's supposed to be built, right? And this is a more practical way of building solutions. When you call a function, you don't try to take too much of precaution, because when you try to take too much of precaution, you're trying to say, oh, this can happen, that can happen. You put a lot of conditions and your code gets more complex, and you might not have handled one corner case scenario in your precautionary measures. Rather, you call the function with that argument, whatever that parameters. The function is incompatible, let it raise an exception, but you handle that exception gracefully. You handle it. If this throws an error, now figure out what to do. And that is the truest essence of duck typing. Right? So this is what I give you. Duck typing is something that takes more time to assimilate and apply in your code. So I just gave you one part of the session here. When I talk about functions in the odds and ends, you'll see much more of it when I show you more examples in the coming sessions, right? So with this, I'm going to end this video here. So I think I covered all the important things that I had to talk about related to functions. So I told you about in this multi-part series, I told you how to define functions, function prototypes, about everything that you need about scope, enclosures, right? Enclosed functions, or we call them as nested static scope arrays. That's what I used to call it, because I read in some documentation that enclosed scope was earlier called as nested static scope. It looks like a mouthful, just like arbitrary argument list, which we simply call as var args now, right? So it's the same way. So terms keep changing. So I covered that. And in this session, the odds and ends, I talked about higher order functions. You know what our higher order functions are, what a pure function is, And now you know what is duck typing versus generalization. The two ways of looking at program design when it comes to object orientation. Duck typing versus generalization, right? So with that said, I'll finish this video. If you really liked if you really like what I'm doing, all these concepts, if you're finding it informative, please do hit on the like button. And if you're not already subscribed, please do subscribe. And I will see you in the next one. Thank you very much.